This is the Magnetic Fields Homework Booklet question number 19. A coil is connected to a centre zero ammeter as shown in the diagram. And a student drops a magnet so it falls freely and completely through the coil. You're asked to describe what the student would observe on the ammeter as the magnet falls through the coil. So what we have here is we have a magnet falling through a coil which causes a change in flux linkage in this coil, which leads to an induced EMF and then a current. Now as the magnet enters the coil, the needle will deflect one way, representing a current in one direction, and as the magnet leaves the coil, the needle will deflect the other way. We'll be explaining why that is in the next part. So, if the coil were not present, the magnet would accelerate downwards at the acceleration due to gravity. You are asked to state and explain how the acceleration in the student's experiment is affected as the magnet enters and then leaves the coil. Now, the acceleration of the magnet as it enters the coil will be less than the acceleration due to gravity. We need to explain how this situation has arisen. So we know that the change in flux linkage in the coil as the magnet falls into the coil causes an induced EMF. The induced EMF leads to a current in the coil. And the current in the coil leads to a magnetic field around the coil. Now, Lenz's law states that the magnetic field that's ultimately induced must oppose the cause. So it must oppose the motion of the magnet falling into the coil. Now, if you look back at the diagram, the consequence of that is that the field generated around this coil must result in the top end of the solenoid being a magnetic north pole. That will then repel this magnet as it falls inwards. Now, going to the next part of the question, we consider the magnet leaving the coil. Now again, the acceleration is less than the acceleration due to gravity. Again, this is due to an induced EMF producing a current and a magnetic field opposing the motion. However, to oppose the motion, now if we look back at the diagram and imagine this magnet below the coil now, then the top of the magnet was a south, so we'll have a south pole sitting here. Now to oppose that falling, we would need an attractive force up here. In other words, the bottom of the coil must now be a north. So we have changed from the top of the coil being a magnetic north pole as the magnet enters, to the bottom of the coil being a magnetic north as the coil leaves. This tells us the direction of the current induced in the coil must have reversed, which takes us back to our original point at the start of the question. Finally, you're asked to consider what would happen if the student had forgotten to connect the ammeter to the coil, leaving an incomplete circuit. Now, the consequence of an incomplete circuit is that current cannot flow. Now, you are asked to describe and explain the difference to your previous conclusions. So, consider the magnet falling. The magnet will now fall with the acceleration due to gravity. This is because, although an induced EMF is still induced, there can be no current because we have an incomplete circuit. That means there will be no magnetic field generated around the coil and no force opposing the motion. Hence, the magnet falls with the usual acceleration due to gravity.